Good morning to all. My name is Yojit. I am from Srinivasa Ramanujan Institute of Technology. Today I am going to walk you through the topic crystal field theory from chemistry. Crystal field splitting in octahedral complexes. In octahedral complexes, the metal is at the center and the ligands are at the corners. Theoretical foundations developed by Hans Bethe and John Hasbrouck van Welk, and the main concept of crystal field theory is the metal is at center and the ligands are at the corners of from the metal ion. It posits that an electrostatic field created by ligands influences the metal ions d orbitals, causing changes in their energy levels. The 5d orbitals in a free metal ion dxy dyz dxz dz square dx square minus y square possess identical energy levels, a state known as degeneracy. Octahedral geometry and the ligand approach. Symmetrical arrangement. Six ligands position themselves symmetrically around the central metal ion, typically along the XYZ axis. Point charge model. Within CFT, these ligands are modeled as negative point charges that approach the metal ion directly along this axis. Crystal field splitting in octahedral complexes, higher energy. The dz square and dx square minus y square, we call it also called EG lobes, and the two E2 T2G lobes are dxy, dxz, and dyz. This EG set of orbitals point directly towards the approaching ligands. These direct alignments result in greater electrostatic repulsion, elevating their energy. Whereas in T2G orbitals, dxy, dxz, and dyz oriented between the ligands, they point in between the axes of x, y, and z. So compare as a result, the approach of these ligands towards the EG lobes is much more than the T2G lobes because of the arrangement of these ligands in between the axis and along the axis. Visualizing the splitting energy diagram, the picture is showing the energy diagram of 5 orbitals. 3 are considered as lower energy set and 2 are considered as higher energy set. Ligand field stabilization energy T2G stabilization. Electrons occupying the lower energy T2G orbitals. When compared to EG orbitals, T2G possess lower energy because the ligands are present in between the axes, not point towards the axis. So that's why they have lower energy, each adding minus 0.4 to the LFSC. EG destabilization. Electrons in the higher energy EG orbitals. What are EG orbitals? Dx square minus y square dz square are EG orbitals. Why they possess higher energy means they point towards the axis of x, y, and z, not in between the axes, so contributing 0.6 per electron. Factors affecting magnitude. Nature of ligands. Ligands are categorized as strong and weak field, impacting the magnitude of strong field ligands. Weak field ligands. It's a complete opposite for strong field ligands. Causes a small delta knot, resulting in high spin complexes where electrons occupy more orbitals before pairing. Example, now we are considering two examples where one is a strong field, another one is a weak field. Strong field ligand is NH3 on the left side. Weak field ligand is F minus, what we are observing on the right side. Electronic configuration is low spin if in the strong field. Electronic configuration in weak field is high spin. Magnetic property of strong field ligand NH3 is diamagnetic. Magnetic property of weak field ligand F minus is paramagnetic. Why? Because they are unpaired electrons considering. Thank you for giving this me opportunity.